Yeah. Okay, hello everyone. My name is Samuel Spinoza. I'm one of the co-chairs of the graduate student community here at OU. I'm a master's student in the School of Electrical and Computer Engineering. I'm working with Dr. Sigmarsson at the Advanced Radar Research Center. And today I'm excited because we are continue we continue with our seminar series, and we have an exciting topic and an amazing presenter for today's webinar. And first of all, just let me introduce the graduate student community, also known as GSC, for those who are not familiar. We are an student organization who supports graduate students through their graduate journey here at OU, and also we motivate undergrad students who want to pursue a degree, a master's degree, or a PhD degree. So we throw different events throughout the semester. This is one of them. So as you know, this semester we're talking about artificial intelligence, and this seminar is intended to give you an insight from a different perspective of artificial intelligence. So let me introduce the team. So there are two co-chairs. There's Ronnie Hurt and also me, Samuel. We have in the publicity team, we have Abinash, Hafiz, Swapnil. Also, we have two co-treasurers, Siavash and Ashu. And our support team, we have Sareen, Roshan, Rachel, Suramya, Viba, and Nuraim. Also, we are mentored by Dr. Farooq Mistry. He also helps us to throw all the activities and events that we have. So we have regular meetings every Wednesday at 6 p.m. So if you want to become a member, it's very simple. You just reach out to us, to Rodney, or you reach out to me. Those are our emails. And also every semester we schedule our meetings based on uh, all the team schedule, so we can change the time. It's not a fixed time or day. So if you want to become a member, there's a QR code over there. You can scan it and join our team on Engage. So it will prompt you to the Engage website, and you just click join. So as simple as that, you can become a member. And also we have our LinkedIn um, profile. So we post every week our webinars, so you can stay informed regarding all the activities and also all the presentations that we have every week. Also, we have Instagram and Facebook in case you want to follow us. And also, we every week we post all the activities that we have. Also, we have a YouTube channel, and in that YouTube channel, we upload all the presentations. So in case you miss one of the presentations uh, this semester, because every week we have a webinar. So in case you miss one presentation, you can go there and you can search that presentation and watch the whole event that we have every week. So we have a Dave and Susan Bird Team Room. So this is a space that we have in the university. So you can go there and you can use all the amenities. You have couches, whiteboard, coffee pot, microwave. So if you want to get access and become a member, just remember, just reach out to Rodney or me. So another reminder, please make sure that you sign the attendance list that we're going to post here in the chat, so we can keep track of all the people who's attending this webinar, and also we can send you more information in case you need to know more about the GSC. So this semester we're exploring research frontiers with generative AI. We're talking about issues, methods, and applications. So as you know, we are talking about AI from different perspectives, from different disciplines. And well, this semester, we are approaching AI from different perspectives. So today is not the exception. So before we dive into today's topic, just let me give you some announcements about the next webinars. So for next week, we will have Karthik Ramani, who's a professor of the School of Mechanical Engineering, and the topic will be physical AI for human-centered perception and action. Then on February 25th, we will have Rohan Doctor, who's the founder and CEO of Louisa AI, and he will talk about using AI to connect people and not replace them. And also on March 5th, we will have Rustam Kanga, who is the co-founder and CEO of iOmniscient, and he will talk about ethics of AI. So without further ado, let me introduce today's speaker. So I'm truly excited. It is a privilege to introduce our speaker today. He is Dr. Sridhar Radhakrishnan, and he's an associate professor at the University of Oklahoma, who has been shaping innovation and advancing research in OU since 1990. And his work has resulted in many protocol development for broadband networks, wireless, as well as radio frequency identification systems. What makes his work especially exciting is his forward-looking focus. So he's currently looking, and working on the development of protocols at the intersection of Internet of Things and software-defined networks, also known as SDN, which are two transformative fields that are redefining how computers communicate and operate with each other. He's also actively involved in the development of algorithms for high-performance computing, especially on desktop parallel computer systems. He has published over 100 research articles in journals, conference proceedings, and book chapters. And his career reflects not only technical excellence, but also a sustained commitment to solving real-world problems through innovation, collaboration, and progressive design. So he will be presenting the topic Rethinking CS through Computational Epistemology. And please, everybody, join me in welcoming Dr. Sridhar.
Thank you. Thank you. Thank you very much. Can I share, Farooq?
Yes.
All right. Well, thank you very much. Welcome, everyone. Today, I want to talk about something that I believe is a fundamental shift in what computer science should be about. The title, Rethinking CS through Computational Epistemology, may sound philosophical, as Marcos pointed out, is a philosophy major too, but I intend to show that how it is deeply practical and urgent. The question at the center of this talk is, what should computer scientists be doing now that the machines write code? So the question, to me, let me start with the question that motivates everything in this talk. Large language models can write code, debug it, configure systems, and handle routine implementation tasks. These things, these things we spent decades teaching students how to do it. So if machines can do all that, what remains distinctly ours? Ours in the sense of a computer science person that I'm talking about. What is computer scientist's job in a world where coding is increasingly automated? I want to argue that the answer is not to code better or faster or efficiently. We still need to do that, but I think we have been doing that. It is to take responsibility of something much harder, knowledge itself. So what I want to say is, to understand this shift I'm proposing, we need to understand what CS was built around. For decades, computer science is defined and centered around something called execution. What we mean by that is translating the human intention into precise executable instructions. We have fantastic verticals, or something that's dear and to computer science is algorithms. compilers, operating systems, networks, and databases. Every core of this field was designed to make machines to do things reliably and efficiently. Knowledge was something that was treated as an application layer. So something that domain experts had to worry about. The computer science job is to build the plumbing. I want to argue that this division is no longer holds. What do I mean by it? Let me tell you why it no longer holds. If you look at medicine, law, science, finance, and public policy, every domain depends on computational systems. Not just to execute the instructions, these systems represent the world, as you can see. They encode assumptions. They support decisions under uncertainty. Computing is just not a tool that people use. It is an infrastructure through which knowledge is created, stored, and acted upon. Okay? So when you have a clinical decision support systems that's going to flag a patient, it's just not computation. It's the knowledge. It's a knowledge claim. Right now, in CS, there is no principled framework for managing these claims that we have. So we need to worry about it. So let me give you a distinction here. People know this. Information is not knowledge. Let's say a database can store a patient's white blood count, and then we find out it is elevated. That's information. But knowledge is something richer. Knowledge includes why this fact matters, what it implies in the context of other findings, as an example, what assumptions it depends upon, when it should prompt a change in a clinical judgment. CS has built incredibly sophisticated tools for managing information, from database to search engines to retrieval systems, but it's not an organized itself around knowledge. This is the gap that I would like to address. To make this point more precise, as somebody pointed out, I've done a lot of networks. I believe in layering systems. So if you talk about this layered systems, as you see right in here, think about how human brain works. I'm not a brain specialist or anything like that. This is just my knowledge. It does not just store facts. It reasons over them. On the computational side, you have layer 0, right? Which is raw and unstructured data from a computer science guy perspective. Layer 1 is data that is organized for information. But layer 2 is the knowledge. The claims that are justified, connected, which claims are connected to other claims, the revisable aspects of this. When does the evidence change, and when do you have to go back and revise something? The human brain, of course, has these kind of analogy 3 layers. You got memory, you got information pockets that you access, and the cognition part. So CS is extremely good in dealing with layers 0 and 1, but layer 2, the knowledge layer, barely exists in the computational architectures. This is the gap that needs to close. Another way to look at it is, whenever we talk about cognition, whenever we want to do recall, we look at pockets in the brain memory to do that. So we need to look at this missing piece of information, which is the knowledge layer. Okay. Now let's look at the current systems that actually stand in these 3 layers as an example. If you look at the traditional database systems, phenomenal, great work. They can do organize, they can do help you retrieve information and so on and so forth. But there is no enlarged language models that you can see. They have no layer 1. There's no structuring. Everything is baked into those weights. They simulate a layer 2, but they do not implement it. Okay. And then what do I mean by that is, because they don't have any kind of inference mechanism. Okay. So I always say this. I'm going to repeat this maybe a few times. An LLM is just like a parrot. Okay. Whenever it sees the cloud, it's a cloudy day, and it sees the rain, it makes a judgment by pattern. It says, hey, whenever it's cloudy, there's no meteorological model that's running behind an LLM system to make that it is going to rain. It is just a pattern. It's just a parrot. So what you're dealing with, all your LLMs are just a parrot, a sophisticated parrot, I would say. Okay. So their training data is baked in, not retrieval and structured. They simulate layer two to generation, but do not implement it. So there are no models to implement this as such. Rack systems, retrieval augmented generation systems, they patch in layer one through retrieval, but reasoning is still generation. It's not a genuine layer two. Some of us in this meeting will know we heard about expert systems. An expert system actually genuinely did layer two. When people actually went and discussed this matter they coded the knowledge, they brought in logic, they brought in if then else conditions. The expert system actually made a really good attempt on layer two. But there, at the time when the expert system was in place, layer one was brittle because there's no way they could digest volumes of information. There is no infrastructure existed to change something when new information came. So expert systems did their job at the time, given all the constraints. So the key takeaway is no existing architectures, all the three layers working together. That's the problem we need to solve. Let me give you an epistemological turn here. CS must shift from programming machines to governing knowledge. That's what I think. Building layer three requires three things. First thing should be representation. How knowledge is represented, how claims are represented, how when you want to revision a claim, what happens. This is actually knowledge encoding. But people have worked on knowledge representation. I'm not going to take away. There are formal mechanisms of knowledge representation. But they have not gone into the factor of reasoning and verification to the extent that I would want them to do. So reasoning is what does conclusion derived from existing knowledge. And third is a verification. So let me go through each one of them in this. So representation would mean what is stored, what stores in rows and documents, and what does layer two store. So here are the primitives. You store claims and assertions and truth values. Justification, links from claim to a supporting evidence, you store that. Which claims are depending upon which premises and which constraints, you store them. And you store the constraints under which certain conclusions are going to hold true. And the revision triggering conditions has to be done on what needs to be reevaluated. So you got symbolic structures like logic and ontologies can provide this explicitness. Embeddings capture patterns that obscure justification, and we got a hybrid architecture that must combine both. And critically, representation is a design problem. It is not a data problem. Each domain carries its own epistemic norms. That's the world in which those domains exist. We need to capture them. And second pillar, of course, is layer two. What does it do? It needs to derive new claims from existing ones. It tracks conclusions based on the premises. It propagates revisions when the premise changes. It distinguishes what is concluded and what is assumed. There are a lot of tools available: logical inferencing, probabilistic reasoning, agentic workflows that are becoming common these days. They have no truth maintenance system. They don't maintain the truth. That's in the layer. There's no separation from assertion hypothesis, and there's no mechanism to retract. LMs can never do any of this stuff. By the way, hallucination is predictable results of generating claims without layer two. In fact, I argue that hallucination is actually a feature and not a side effect. Hallucination is important. And whether you got to go take what is hallucinated as a claim and verifiable system, that is what is needed. All right. The third pillar, of course, is verification. We need some provenance chains, for example. A correct answer without justification is unreliable. You cannot trust it because you cannot inspect why it is correct. And explainable AI. I mean, there's a lot of things. I got experts much more knowledgeable in all of them than I am. Explainable AI only trace you how the input is transformed all the way to the output. It doesn't tell you the domain constraints, the logic, the claims, and how it connected together. It doesn't do that. A justified answer is traceable evidence is trustworthy. Even the later finds an error because you can trace back and fix it. Verification requires provenance of claims from evidence to every transformation. Very important. So the bottom line is trust must be earned by architecture, not by output. So now, in computer science is deep rooted in these, and we know what is possible and what is not possible. So we have amazing things that deals with the Turing halting problem, the semantic properties from Rice, it's called Rice's theorem, and Gödel's theorem. So let me give you an idea where I'm talking about. What Turing says is that if you build something on layer 2 and then says there may be a chain of inferences, claim A leads to claim B, claims to claim C, and so on, what it says is the following. You cannot have a model that always decide whether it's owned. You can't guarantee that a process will terminate. You can go to claim 1 to claim 2. We cannot guarantee that it will terminate. That is, you cannot build a general purpose monitor that says, if you ask a question, you can find all possible claims. That's what it says. So you cannot be verified by the system. That's why you need a human in the system, in my opinion. So the human in the loop becomes important. Now, what does Rice say? Rice says this is important. Suppose you want to ask a system, this output is justified. So basically, you're asking the semantic property of the output. It's about output means, not the characters in the output. And Rice tells me no general algorithm that can inspect its own output and verify the kind of property you're looking for. What does Gödel say? Well, this says it cannot certify its own soundness. It cannot prove that from within its inferences are valid. It will always be blind spots about its own reliability. So what do you combine? Turing says the system cannot guarantee its reasoning. We'll finish. Rice says the system cannot verify what outputs mean. Gödel says you cannot prove its own reasoning system is sound. Oh, man, actually, every route is blocked. So you cannot build a system that monitors its own termination or its own semantics and its own consistency. So self-verification is not a hard engineering problem awaiting more compute power or more better architectures. It's mathematically impossible in a general case. So given that you cannot say, I'm going to automate everything away, so it's beyond computation. So limits do not stop us at computation. Even system that could somehow verify its own output cannot determine whether the objective is the right one. So we need to set goals and values. And you need to talk about risk tolerance set by people and institutions and not by models. Who decides this false negative is okay? This rate of false negativeness is okay in a diagnostic system. It's a human judgment call. And epistemic failures do not stay contained. And an ungrounded clinical claim, for example, if you feed into an insurance system, and the insurance system will shape policy based on that, then you are going to have conclusion that's going to propagate. Not a good idea. We need human oversight. It's not a temporary patch, I would say. We need to be human in the loop, in my opinion. So now come to the point that a computer scientist is a knowledge architect. Okay, they decide what system should know. Just as importantly, what it should not claim it knows. Okay, so that should decides representation that preserve meaning, justification, and constraints. Understands how knowledge is structured in various domains, not just learn to code, but understand knowledge in domains. Build systems whose conclusions are inspectors challenge revise. Computer science is no longer just a coder. A computer science is an architect of computational knowledge. I've been thinking, if I had an idea that if I teach a course called data structures, I've been teaching that for many, many years. And I asked my students the last 3 semesters that they could do LLM to code it. I got and I make sure that knowledge that supposed to gain are done in exams and quizzes and other things. They're not supposed to use any of the LLMs to do it. I feel guilty about it. So if I have to do ideally, I'm going to be language agnostic when I teach. I will have a first course, instead of having a course in programming, I'll have a course that says, I'm going to teach you prompt engineering. I want you to go ask a system to write something in a language. Doesn't matter what the language is. I want you to be able to read code. I want you to know how to have the appropriate infrastructure to implement that code. That'll be my first course. The second course will be a little bit more intense, where I'm going to teach you how do you go to a domain or whatever, gather specification, and from specification translated into things that needs to be done. Then how do you go back and learn about formal constraints and then have a system that you can build? Data structures, I truly believe, not going to change. It's going to be traditional, but I'm going to have epistemological context to it. For example, I would not only teach existing data structures, I would go talk about what are knowledge structures? How would you justify the organization? So operating system, talk about agentic and AI workloads, computer organization, hardware constraints and knowledge processing, database management, provenance, knowledge repositories, algorithm analysis, reasoning complexity. How long does it take to reason something? Inference costs. Specification is an epistemic commitment for software engineering. Distributed knowledge. Theory of computation becomes more and more important, in my opinion. Dr. Antonio used to teach that course, by the way. Decidability limits on self-verification. I will have a different course on computational epistemology and domain knowledge, encoding domain structures. A curriculum is not replaced, it is reframed around knowledge as an organization principle. So open research question, what are the primitives that you should have for layer 2? What are the operations that you perform in layer 2? How do you audit it? What is the cross-system integrity? None of this exists today. All of them are computer science problems. So I want to go back and ask the fundamental question that we start off with. We want rethinking computer science. If machine can code, what is the computer scientist's job? I think to decide what computation systems should know, to design how they represent and reason, to ensure that the conclusions are justified and governed. The future of computer science, not writing better code, is about building better knowledge. With that, I conclude my presentation. Thank you for listening. Thank you.
Well, thank you very much, Dr. Sridhar. I think that last phrase was the summary of all the presentation. And of course that probably makes people thinking about what's the next step, or how can we approach that problem. So I'm going to open the floor for questions. So please keep your questions brief, and then Dr. Sridhar can answer them. So if anybody wants to ask a question, please just unmute, or you can write your question on the chat and I will read it.
I guess I have a question, Sridhar.
Yes, sir.
It was a very good presentation, really stimulating.
Thank you.
When I think about, large language models, and yeah, they very good, it seems, at programming. Do you think part of that reasoning is, being a parrot, or just sort of finding those patterns is easier in the context of a context-free language, right? A CFG, relative to natural language and human communication, which can sometimes be irrational and ambiguous. So I guess have you thought about that and kind of?
Yeah. I think 100%. Okay, so the beauty about this is that 100% correct. If you have a context-free language, it's able to do it, but it just not The context-free language helps them to verify the code they write. It is in the grammar wise, it's correct. It does not check the semantics of what the output is. That's unable. It can't do that from the theorems that you've seen. But it cannot reason out why this program works that way. But it can give you syntactically correct ones. The reason that has happened is because there are volumes of data they have obtained that was otherwise not possible in the past. And I'm glad that you bring that. So semantic meaning of something is extremely hard to decide whether it's English or not. But even in English, while English is a context-sensitive language, for the other audience, I'll say you can say John shot a buck. Depending on the context, John shot a buck would mean that, hey, he got $1. But it could be somebody killing a Bambi. You can talk about Venetian blinds in English. If an interior decorator, it's one that you put on windows, it's called Venetian blinds, or blind people from Venice, for example. So context matters. So what they have done in all this language model is to make sure that you put yourself in the context. So less and less undeterminism plays a role. The answer is right. Context-free grammars are useful, but only for syntactic checking. It has not been useful for the semantic aspects of it, what the meaning of those things are.
And kind of related to that, thank you. When you think about knowledge and sort of this absolute logic and rational, I feel like it applies, it's the easier problem is sort of kind of physical sciences knowledge, things where we at least have some pretty good evidence on what the first principles are, as opposed to kind of the social domains of politics and history, where it's blurry and messy and people kind of have their own. So I don't know, just kind of trying to think about knowledge and how it can be kind of subjectivity, and especially when you start bringing in the human factor, it gets really messy. I think another thing that struck me when you said, I would push back a little bit that humans have this deep knowledge of everything. We also act like parrots, right? So when a toddler learns to walk, she's not doing differential equations in her head and thinking about the stresses on her bones and have this really deep granular knowledge of, which is, our understanding of why she can walk. She's sort of just watching her parents or her sibling and kind of trying to imitate that at a very high level. And so in some ways do you really need to know the knowledge, or, again, it gets pretty philosophical.
No, it's philosophical. I think what I believe in the human side, we build a model, though. We execute it on the model. We don't able to convey that model. Because reason we are able to execute, I think that we build a model is because we teach somebody what we learned. The ability to do that and give a rationale why what we do is correct. I think we have built a model in our head. It could be based on patterns or experience. And I think your point is well taken. In physical stuff, in engineering, for example, we measure something, we know the outcome, and from first principles, other things we measure. In the social sciences, extremely hard, right? I mean, it's all individuals, how group of people will behave in a particular environment. How do you model that? It's a hard problem, I would say. But you're right. Parroting is, you can build a model. I mean, let's say it's a cloudy day, that's built into an equation of a less sophisticated model, but over time you can keep building more sophisticated models. Yeah, great point. Great, thank you, John. Marcus.
Marcus, yeah.
I appreciated you drawing out the need to reconsider how we do computer science education right now with prompt engineering. But I was thinking back to, in the 90s in grad school, I had a fellowship in knowledge engineering. Yeah. And I feel like that's kind of, a lost field. I don't think, as you pointed out, current AI has that as an objective or a goal. it's kind of discarded. So I'm wondering what your thoughts are about, sort of reviving that field.
Oh, I'm glad you brought it up. I don't think so that we have lost what is in knowledge engineering. I think knowledge engineering provided aspects of what we want to do in the full epistemological sense. What knowledge engineering gave us was, let me teach you some mechanisms to encode knowledge, for example, right? We learn that in some sense. So I believe that what you are saying is perfectly correct. Knowledge engineering that we have done before could be used in this environment, but just for parts of the encoding process. They haven't done the whole slew of, how do I draw inferences? How do I do this? So I think you are hitting right on the money in there. I'm glad that you're talking about this knowledge engineering stuff. I remember a course like that in the past as well. So very nice, very nice. Yeah.
I have a question, Professor. So, thank you for your presentation. It was wonderful. I just want to say, when you work with layered architecture and with different context, have you considered ontologies in that matter? Have you considered that if we take into consideration different ontologies for different contexts, would it be easier to define a context in the term of a specific ontology?
I mean, ontologies, as Marcus point, not ontologies are one way that we can store knowledge. So the how you store knowledge in different domains is going to be different, in my opinion. So ontologies are going to be those domain specific, and that's part of the knowledge representation layer. Okay, so that's that, and that's the answer is correct. It will be part of the knowledge representation layer. Yeah, yeah.
Thank you, Professor.
No, thank you.
Uh, I also have a question. Thank you for the nice presentation.
Uh,
So my question is, like, in scientific modeling, like especially other fields than the CS, like especially in physics driven or physics based systems, like we already encode assumptions and constraints and revision uh, logic explicitly. So would that be a more practical starting point for building layer 2 architectures? Oh,
100%.
okay. Like
Yeah,
instead
I
of
think
jumping straight into a general purpose.
yes, ma'am. I think you're right. Yeah. So, we have basic facts in every domain,
Mm,
especially the domains in which that the claims can change over time. This one classical example that epistemologists will say, let's say I have an hypothesis, a couple of hypotheses. And one of the hypotheses is that every integer that you're going to see is going to be an even number. Okay. And then second hypothesis that every integer you're going to see is going to be divisible by 6. So you go 6, 12, 18, 24, 30, and so on and so forth, right? The second hypothesis, if you get all the integers are going to be like that, which is multiples of 6, then it's also the first hypothesis is true. Let me tell you what I'm thinking about. So, but if you say suddenly you stick in a number, let's say 24, right? In that 24 is an even. The first hypothesis is true. The second hypothesis is false. What the idea is, the claims could change over time. If you haven't seen enough evidence now, up to this point, the claims may be right. So whatever that you encode using the laws of physics or whatever it is, right? Which laws of physics doesn't change. But I'm just saying for engineering work, you go up to a point, your claims are, but the claims could change if you have more input in the future. In fact, one of the things they say is that you won't be able to decide which claim. That's the knowledge up to infinity, they call it. You cannot say something is going to be true for knowledge up to infinity. So that's what epistemologics will talk about. Yeah, but right now, for practical purposes, we encode what you know. And then the idea is to adjust these claims as new inputs come becomes more and more important.
Right. Thank you for the nice
Uh-huh.
explanation.
I have one more thing to say. I did join a little late, but I felt like your talk was very much similar to that three-layered data architecture in knowledge graphs that we see, like the storage, and then we are extracting and transforming,
Sure,
and
yeah,
then
sure.
and
I'm sure
display and application. Yeah.
sure, it should be motivated. That's why it should be motivated from there. Yep.
Yeah. This was really nice. Thank you so much, Professor.
You're welcome.
We have one more question. You can unmute.
So I have one
Yes.
question. It was
Okay.
great presentation, Sridhar.
Thank you, Pejman.
Just, of course, one question that actually the final point that you say, for example, the future of CS is not writing better code and kind of is building better knowledge, like what you is kind of saying. Do you distinct between like the better code and better knowledge? It's kind of somehow when you say building better knowledge, better code maybe give you better knowledge. How you actually, is it kind of the focus should be on having a better code that can better generate better knowledge, or it's kind of, can you clarify?
Oh, that's good. It's a good point. If is better code, if the question you ask, I'm going to reframe that. Okay. So if you have good knowledge, can you write better code? Can you will better code enable to produce better knowledge? I think I agree with on both those points. The reason better code can give you better knowledge is that sometimes knowledge has to be retrieved from stuff. So a better code can retrieve the knowledge that you're looking for, right? So that you can gain that knowledge. If you have good knowledge, you can ask systems to write better code for you. So that's what I would say. So I think both are correct. Both sentences are better code produces better knowledge produces better code. I agree.
Okay, good. Okay.
Yeah, agree with you.
Thank you so much.
Welcome, Pejman.
Professor Naidu, you can ask your question. Yep.
Yeah, thank you, Professor, for very good presentation, very interesting, and gave a very not fully philosophical, as you rightly point out, but a sort of a very interesting perspective of computer science.
Thank you.
I come from the expert system era, so I am aware of what you are telling about, because we thought that many of the things what is claimed by AI and machine learning, we thought that we were there in the 90s. But then it went back because of the computational limitations of those times, I believe.
Correct.
So my question is, because I am basically a mechanical engineering designer, I started my career from that. And my question is that we have large language models, but we don't have large drawing models. For example, like engineering, like we used to say, drawing is the language of engineers, right? So particularly for mechanical engineers. So now the drawing is very well specified, very well defined. I think computer science should be able to capture a drawing and create new drawings for new applications, or maybe similar scaled up applications, scaled down, that should be easy. But improve the drawing, improve the design itself through improved drawings by artificial intelligence. But I think the full focus is large language model, but not large drawing model right now. With your philosophy, how do you look at the future where maybe designers can be helped, assisted, or maybe even replaced one day by some sort of a large drawing models? Thank you.
Thank you. And and as Dr. Antonio was pointing out, I think drawing is actually, drawing can be expressed as a context-free language. And I'm surprised to hear that there are not AI generated mechanisms that they give you, ask a CAD question, it generates a CAD diagram for you, satisfying some constraints, for example. I'm surprised there's not one. So if somebody starts one, you'll make a lot of money doing that. And I think design as such, is the value of a design, an outcome of a design, it is such personal to me. So when you have personal choices, what likes and dislikes, I don't think so that you can justify that. It gets into philosophy, psychology of, not philosophy, psychology of people, that what one likes, one doesn't like. So design is a much harder problem, but producing a diagram, an engineering diagram, I think that can be easily done. I don't know why nobody has done it. I don't know. I have not investigated whether somebody has done or not. I think this should be easy, in my opinion, to do. No.
Yeah, thank you for your answer. Just to add to that, just for thought provoking. So you touched upon the personalized aspect, which is the aesthetic aspect, which is more relevant for product design or industrial design, because it captures one's like and taste and all. But then there is this boring mechanical engineering design where optimization and that sort of stuff is there, where the strength of materials, it should last, it should be durable, and it should have the required strength and stress and all that analysis. So that needs to be sort of very much supported by engineering mathematical, maybe some sort of, you can call large language model, large formula model, I don't know, something like that. But the aesthetic aspect definitely is also a consideration where generative AI is doing something, but not fully. So, but thank you. There's a lot of scope for work there, it seems, in the area of design and engineering drawings.
Sure.
Thank you.
Sridhar, I have a quick question. Hi, yeah. I think it's kind of following through along other people's question too. So you mentioned when large language model gets so popular, people don't need to learn coding as much, but rather focus on architecture design, right? So I have this question actually battled me for a long time about how we shape our education. So my understanding, we are all from old schools. My understanding is to build knowledge, to have that cognitive thinking, eventually can have architecture design ability. You need some basic fundamental training, right? Go through maybe tedious coding process, debugs, and make mistakes and then correct it. But right now, with this large language model, everything, like a lot of people can bypass those training process, right? Already achieve the result we want. So how do you think we can educate our next generation humans to stand at the level you mentioned in your slides without or bypassing a lot of tedious work we are talked about?
Yeah, great question. In fact, in my mind, it's all about how we are going to educate. And the whole thing is, how am I going to teach my students? I've been toiling with this data structures course. I'm going to timestamp me by saying, age stamp me. I have taught that course for 56 semesters so far. And it's more exciting now the last 4 semesters because of the availability of large language models and how much more information I'm able to impart to my students. Otherwise, I could not have done. So I think I am more optimistic than before. So now ask the right question. What are we supposed to teach our students? I truly believe design you talk about, engineering constraints you talk about, and I'm not saying this because my dear colleague Janet Allen is here. Systems engineering becomes extremely fundamental. As an engineer, you got to know how you need to put the systems to put together and reason out why you do this in a way. I think fundamentally, I would just go back and say, let somebody do the grunt work. Let people acquire, how do you go to a different environment and domain, acquire knowledge, turn the knowledge into specification? How do you go worry about storing that knowledge? How do you build systems that can integrate all of them? Fundamentally, that systems engineering is I think it's very important that we should educate all the engineers, not just mechanical. I would even say computer science people should know about systems engineering. I think we have failed in that. I can say it, I've been a professor for too long. And I think we have failed in that. I think that we have not educated our engineers and computer scientists the right way. I think it's time to think about this.
Yeah. Great. Thank you for your insight.
Thank you. Okay.
Thank you so much. Actually, one point that I want to say, I don't have any question, but you made my day because the way that you present, I could say our work is not identical, but is in the same direction, expressed in different languages. The things that I could say, I see a strong connection between your talk and my dissertation, because you describe a gap between data system and knowledge system. And in our work that we are doing, in my work, especially in SRL, I focus on structuring predictive output into traceable, uncertainty-aware constraint before they influence decision. I don't treat AI as a decision-making. I treat it as an information source that must be, for example, governed through explicit rule and human responsibility. In page 15, you mentioned the computer scientist is no longer just a coder. The computer scientist is an architecture to computational knowledge. So, for example, the way that I am doing in the SRL, we are not building a better forecast or solving a problem. For example, optimizing supply chain costs or applying, for example, machine learning. We are trying to design predictive knowledge that should be structured, bonded, translated into the constraint, and audited before decision-making by human. So when you present, it shows the importance of my way and makes me more motivated. Really appreciate and so happy to join. Thank you.
I couldn't agree with you more about systems. One of the things that is clear is that we have spent a lot of time on methods of analysis, but we haven't spent enough time on methods of synthesis in general. And so we have to be able to think actually in different ways to tackle the problems you advised.
Yeah. Yeah, I mean, I was blessed. I have a master's degree in system science, actually. And I was taught many years ago. I won't timestamp me, but this many years ago. So I think that's an important thing. I think we need to be able to. But I'm not calling for drastic change in computer science. I think computer science lives forever. I think we need to elevate ourselves, not be worried about. Marcus goes to an environment where rubber meets the road, right? I mean, businesses, banks have knowledge, bank personnel have knowledge. How do you encode that knowledge? How do you come to a conclusion? So programming is just a vehicle. I mean, I remember in computer science, we had a course called assembly language programming. And then people started writing in Fortran. All the people, Fortran programmers, were called assembly language people called Fortran programmers. You guys are cheating. And we got C. All the Fortran programmers, because you have to column 1 through 5 is this, column 6 is a continuation, you have to call in column 7. All the C programmers are cheats, right? And all the C programmers are saying, all the Python programmers are use libraries, you are cheating, right? Now we are using natural language to program. So what's the problem? So I am saying that it is not. It is actually, it's a better way to program. I think I am convinced that there are more better things to do. We can go elevate yourself higher and higher levels of thinking. Thank you for everybody. Thank you.
I want to piggyback on what Janet has said and what Sridhar has said. Sridhar, you've only mentioned half of what is needed. That is system science. That needs to be coupled with information science.
Right. Yeah.
Because if you just do system science, then we will end up again with the same thing. These are the problems in systems. Let's solve these problems. And we'll again go into the problem-solving mentality instead of thinking in terms of framing the problem. And to be able to frame problems, you need both system science and information science. So what is your opinion of that?
The reason is I know information science is important, but because I'm a computer scientist, we deal with information science all the time. But and I'm not sure how I can separate that as we do information science. Computer science is an information science. So I'm not sure how to separate that, but the answer is correct. I'm just saying the marriage between, I use the word system engineering is because if I want the students to graduate and get a life, I think they have to do engineering work, whether it's software engineering or whatever it is, that's life. So I would say get knowledge about systems in the sense of deployable systems in the information science world. How do you deploy them? How do you connect them? How do you do this? I think that's important. That's where I come from. I think you're right, but I take it for granted because we in computer science do information science. Yeah.
Thank you.
Perfect. Professor Sridhar, I have one question. So it's like a follow-up regarding some questions that we had. So do you think that this could be an advantage? I mean, if we focus more our energy in teaching how to solve problems or how to deal with the upper layers and not just bypass or skip the layer 0, but emphasize more on upper layers, do you think that that could be an advantage compared to previous systems or previous way of teaching?
100%. It's a huge advantage. In fact, I think nothing is, because when you talk about the higher levels, we do that in a computer science curriculum. We don't give them formal mechanism. Engineers do it too. We give them a context. The context is the domain. The context is what that we are talking about. The context, we are saying the context, you think about coding that context, right? Engineering design.
Yeah.
You build a bridge where there's a soil dynamics is this. It's a different than when you go to another place, it's going to be rocky conditions, right? It changes by the environment. You put a context to it. The context defines the domain that we are talking about. That's where the knowledge acquisition comes. So what computer science people should be, take that knowledge, how do you encode that knowledge, how do you capture that knowledge, how do you make inference out of that knowledge? Fact that information is already going to be stored. That's what I'm pleading. Okay.
Perfect. Okay, I think we don't have more questions. Well, I thank you. Thank you again,
Welcome. Thank you.
Dr. Sridhar. It was an amazing presentation. I'm sure that we have so many questions, and of course that this is a very thought-provoking topic, and I really like that it is also related to a philosophical point of view. So thank you very much. Thank you all for attending this seminar.
Thank you.
And we hope to see you in the following webinars. Have a nice day. Thank you.
Bye, everybody. Thanks, Farooq. Bye.
I'm going to stop recording.